Okay, so our next speaker is Willson from Iowa State University, and he's going to talk about reconstructing certain phylogenetic networks from the genomes it leads.
Thank you. I'm going to be talking about evolution of networks that are not necessarily trees. For example, this kind of a network. You already heard about one standard approach to trying to build networks. So different genes can give rise to different phylogenetic gene trees, and then you're looking for some network that might contain all those trees. Here's an easy example. These might be the gene trees, and you're looking for a network like that that displays them both. But there are some difficulties with that approach that Simone talked about. Often there are many networks that can explain the trees, so you have to choose among them. The most common criterion has been choosing one that has the minimum number of hybridization events. But of course, that's an NP-hard problem, as was shown. And it isn't really clear biologically that that's the right criterion. So that's giving you some kind of a lower bound, but it perhaps isn't the biological criterion you want. This talk is going to involve a different approach. I'm going to try to model in a very primitive way evolution directly on a network that might not be a tree. I'm going to assume the network itself is the underlying description of the evolutionary history, and then I'm going to try to reconstruct the network from data. So a summary of the talk is I'm going to try to prove theorems, because I'm a mathematician. In order to prove the theorems, I'm going to have to make absurd assumptions, perhaps, very strong assumptions. I'm going to restrict the network, so it's going to have to satisfy some conditions. It won't be the most general possible network. And I don't feel that bad about those restraints. On the second, I'm also going to have to assume a very unrealistic model of evolution on the network. But then, once I know the genomes at the root and at each leaf in this network, for example, I'll show you how to reconstruct the network and the genomes at each interior vertex. So let's talk first about the assumptions on the network. I'm going to assume that relationships are given by an acyclic rooted direct graph, such as this. Note two kinds of vertices. There are hybrid vertices that have at least two incoming arcs. And then there are what I call normal vertices or tree-child vertices, which just have one incoming arc. Here's a situation that I don't want to see in the graphs that I'm talking about. So there's an arc from X to Z, but there's also a directed path that goes some other way, leading from X to something else and then to Z. I'm going to call that a redundant arc, and I'm going to assume that in the networks there won't be any redundant arcs. We're going to be talking a lot about base sets, which are going to change during the construction. A base set is a set of vertices that essentially mean ones that we think we know the genome of. It will have to include each leaf, so 3, 4, and 5 will have to be in the set X, the base set. We'll have to include a root, although you can substitute an outgroup for that. And it's going to have to include a vertex like this, which has out degree 1. Something has to be done to specify that particular vertex, and we'll assume that if it's like that, we know the genome. A directed path is called a normal path if every vertex after the first is a normal vertex, something that isn't hybrid. So 10, 12, 15, 5 is not a normal path. Doesn't matter what 10 was, but as we went through this, it went through vertex 15, which was hybrid, not normal. So that's a bad path, not a normal path. On the other hand, 10, 12, 14, 4 is normal. Everything after the first was normal. If you start at a hybrid vertex and follow a normal path as well. So there's one. So a network is going to be called normal if from every vertex there's a normal path to some member of X. This is an example of a normal network. It turns out to be a very strong constraint on the networks. So that's going to be the principal constraint on the networks. What about the model of evolution? Okay, we've had a lot of talks in which we're trying to be very realistic. This will be the opposite. I'm going to assume that each character is binary, with just zeros and ones. Since we know the root, I can just sort of normalize things so that the genome at the root is all zeros. Maybe vertex 4 has this genome. So these, out of the 10 characters, certain characters have changed to ones. This case is the 3rd, the 5th, the 9th, and the 10th character. In that case, I would say the set M, the mutated characters, are 3, 5, 9, and 10. They identify which characters have changed from the state at the root. We'll be using M of V a lot. So what's the model? The basic principles. First of all, some characters mutate at some places like so if a character first appears in a mutated form at vertex V, you put it in the set O of V, the originating set. And so we're going to first assume that no character originates more than once, so there's no parallel evolution. That's a little bit like the infinite line assumption, pretty common. Here's the assumption I'm a little bit embarrassed about. Suppose V is normal. We're going to say that it's going to inherit every single mutation that its parent had. So it'll have everything that the parent had together with the stuff that originated right there. So 12 is normal. We're going to assume that its mutated set will be everything that 10 had together with what was originating at 12. And then since you have the unions, you can start to combine these into longer chains. On the other hand, for the hybrid vertices, we're going to make very weak assumptions. So if V is hybrid with these two parents, P and Q, we'll say that what it gets is something from P, some stuff from Q, and then whatever originated at V itself. So that's a very weak assumption. The idea is to try to see what's happening at the hybrid vertices and how that influences things. There's one proviso. Suppose we had something that originates at 13. So it's all zeros until you get to 13. It's possible that it wasn't inherited by 15 because 15 is hybrid. And if that's the case, the only place it's actually observed would be at 7, this leaf. On the other hand, if something originated at 7, the only place you'd observe it is at 7. So there's an ambiguity. You might say, well, stop. You can't solve the problem of reconstructing the genome. But in fact, you can see, you can always recognize that and say, well, we'll always, in this talk, resolve that ambiguity by saying it would have occurred at 7. We're going to say there are no immediate homoplasies, so if something appears at the parent of a hybrid vertex, then it has to be inherited by the hybrid vertex in order to be counted as there. Okay, so in the special situation where the child inherits all the mutated characters, this is actually a model which has been in print. That's the accumulation phylogeny of Baronian steel. So there are going to be two main theorems. This is the weaker of the main theorems. So we're going to assume the network is normal, as I've described it. I'm going to assume that M of X is known for each member of X, the base set, that the leaves, the roots, etc. I'm going to assume the simple homoplasy model. Then if you know the network, in this first case, if you know the network, then you can reconstruct the genomes everywhere else. So you can figure out what M of V was everywhere. You can figure out what O of V was everywhere. I'm going to have another theorem soon in which we reconstruct the network, but it's going to have some additional assumptions. So if you find the network in some manner, and then you were trying to reconstruct some of the internal things assuming this model of evolution, you can do so without the additional assumptions that are going to come. But I would want to point out that the hypothesis on normal paths is needed. Here's a network that is not normal. You can see if you start at 10, you try to get to a leaf, you've got to go through a hybrid vertex. So this is not normal, just one exception to the normality condition. But one can't distinguish between something being in 9 and something being in 7 but not having the stuff being carried over to 4. So you wouldn't be able to find the genomes at interior vertices for this with just one exception. So what are the additional assumptions so that I can actually reconstruct the network itself? Well, the first assumptions are essentially the same as what we've had before. Normal network, simple homoplasy model, hybrid vertex has just two parents. And we're going to have something present. You know, something will have to originate at vertices so that we can detect them. We're going to have to assume some separation of the hybrid vertices. So for example, if C is hybrid, then its parent has to be normal. We're not going to have that the parent of a hybrid is hybrid. And we're going to assume that the parent of a hybrid doesn't have another hybrid child. So these are a little bit too close to be resolved by the simple results I'm going to obtain. Moreover, there's a condition on the grandparents. If H is hybrid, then you don't have that a grandparent has another hybrid child, or it has another hybrid grandchild. So we're getting some separation of the hybrid vertices. Here's a condition I found very odd that I needed, But anyway, suppose V is hybrid with parents P and Q. I'm going to have to assume that something in the genome of P didn't get transferred into V, and something in the genome of Q didn't get transferred into V. So something was lost. That seems reasonable if you can think of this as being some of the chromosome from P go here, and some of the chromosome, complementary part of the chromosome in Q goes in there. So there should be some loss. Then here's the final assumption. Here's something which I call a pseudocycle. Let's start at the parent of a hybrid, go into the hybrid. There's another parent. Let's go backwards to the other parent. And now let's follow a directed path, and we get to a hybrid. Let's go backward to the next parent, to its other parent, follow a directed path, we get to a hybrid. Continue like this, and whoops, I've been able to find something so that I return where I started. That's a little bit like a cycle. It's not a directed cycle, but it doesn't conflict with the assumption that we have an acyclic graph. Nevertheless, it's very similar, this kind of situation that's been looked at by some other authors. And I'm going to assume that you can't have a pseudocycle. I just need that one point of the proof. So what's the main theorem, too? This is really the main theorem of the talk. Suppose we have a phylogenetic network that satisfies those 8 conditions. Suppose we know the genome for everything in the base set, then we can reconstruct the network N uniquely. How do I do this? Well, here's the major tool. The major tool is something called what I call a stem function. So given 3 members of X, A of capital X, A, B, and X, I'm going to compute this thing, delta X, A, B. And it's the part of the genome of X that isn't in A or B. So since you know these things are in X, you know each of these things, that's well defined, you can compute it explicitly. And then there's another delta, just the intersection of all those things. So the main idea is that if you know the members of capital X and their genomes, you can compute this thing. And it turns out to be a nice thing. So here's a first lemma. Suppose X is a normal leaf with parent P, and suppose P has another normal child, distinct from X. Then what is delta X? It turns out to be the set of things that originated there. We can identify them. The proof works very simply. You take a normal path, which we know exists, from C to something in Y, and then it turns out that the delta X RY, where R is the root, gives you. Moreover, what's really neat is that was just one case. For every leaf on one of these things, delta of X turns out to be O of X, not just the normal leaves that had that spatial property. And if X is not a leaf, then we get the empty set by doing that calculation. So that means essentially we have a computable way of detecting when in some just big cluster of things we have a leaf. Versus when we have an internal vertex. And what can you do? Well, suppose we have a normal leaf with parent P, as in here. So we can compute delta X, and it tells us what originated there. Now, this was the assumption on the inheritance. You just turn that around, you can see that the genome of the parent is what was in M of X that wasn't in O of X, by the assumption this is disjoint from the other things. So we can just remove them, M of X minus delta X. So what does that mean? We can compute the genome of the parent in this situation. And that's what we're going to do repeatedly. So here's a network. X is, in this case, the leaves and the root. Let's just start with one particular example. We pick one of the leaves. We don't know which one it is. Let's say it's 4. We compute delta 4. It's non-empty. Aha. So that means I know its parent is going to have the genome M of 4 minus the thing I computed. So I know that the genome of the parent. So I'm just going to remove 4 and insert 18. So that means 4 has disappeared there. 4 has disappeared here, but 18 has been inserted. After all, we know its genome. OK, so now we take another thing, and I chose 3. We know that delta of 3 is O of 3. It's non-empty. So now we know the genome of its parent. Genome of its parent is computed. We computed. Now, that's something that already was in the network. It's the same as 18. So we remove 3, and of course, we're remembering what we're doing. So that disappears. And now we can just keep on doing the same process. We get down to this, and it turns out that delta of 22 could be non-empty. In that case, we just do a little flip. We add an extra arc to something where this is just the O of 22, and this has O empty set, and then we can remove it. So now we've reduced to a network that, in this case, looks this way, and we can see that delta of y for every member of this set X now is empty set. So what I've told you about so far stops. You can't go any further. But in this particular situation, something very interesting happens. So here's the first lemma. In this in general, suppose that all the deltas are the empty set. Then you can prove there exists a hybrid leaf X with parents P and Q, such that X is the only child of P, X is the only child of Q, and a bunch of other things hold. That the only way to get delta XAB equals empty set is if they're P and Q. Well, that's what is that finding? That's saying that in this situation in general, there's going to be a hybrid leaf so that the parents are in X. And then you can, that's really essentially an if and only if. This is what's most interesting to me in the talk, that there's a criterion to recognize when hybridization occurred under this model. So if, in this situation, all these deltas are the empty set, suppose we find that delta X, P, Q is empty, but the only way that you get the empty set is from that particular collection, P and Q. Then it's a hybrid leaf. Those are the parents, they've been identified, and X is the only child of P and X is the only child of Q. That's a hard thing to come up with, a criterion for hybridization, and most of the assumptions were made so I can prove that lemma. Okay, so we're back in this situation. We know that now that 22 prime is hybrid. We know its parents, so we can just remove that. And now we're back in the previous situation. We can just start doing other things. Here was another hybrid vertex. We separate. We get down to that. Every delta is an empty set now. If we use the lemma again, we identify the hybrid, and we just keep going. And we've reconstructed the network. Exactly. And then from the previous theorem, we have all the genomes along the way, although I think we constructed them here. OK, so now when I did this, I thought this is an absurd assumption on evolution. And this morning I thought it was even more absurd after all the talks. Nevertheless, what I did was it so absurd that I shouldn't talk about it. So I implemented this in a computer program with real data. And we've already looked at this data a half hour ago. And so here we have the Rokas data set on yeast. This is the tree found by Rokas. Holland, Huber, Moulton, and Lockhart looked at a consensus network. And here's their consensus, one of the consensus networks, the very ones that Daniel showed. So we have these kinds of things. What happens on the computer implementation? Well, I get a very, very strong signal for this network. It just keeps on, the little parameters you introduce, you keep modifying the parameters, they keep coming up with this particular network. You can just see it's finding exactly this, and then I don't get a strong signal for this one. But everything else is just as though this were straight. And of course, this is under a model of evolution, not just saying, here's an interesting way to look at splits. This is what is happening in terms of evolution, if you believe simple model of evolution there. And then I just want to point out there's a comparable theorem for reconstructing the networks just using distances rather than all these character assumptions that I was making. Well, what are some further things I'd like to do? Well, of course, I'd like to have a much better model of evolution. So I'd like a better way to identify it as a hybrid. I'd probably be able to drop a bunch of hypotheses if I got a better way. I believe that these normal networks are a nice family, but maybe there's some other interesting, equally interesting, or better, perhaps more biologically plausible families for which you can prove some things. I'd like to be able to deal with homoplasies. I'd like to, maybe even a Markov model. I'd like to give thanks to the Isaac Newton Institute for letting me be here. I'd like to thank the organizers, both of the program and of this particular workshop. And finally, thank you for your attention.
Does anyone have any absurd or unrealistic questions for Steve?
Yeah.
Yes.
Suppose you don't know the genome in the root, how far they will go for this reconstruction.
Well, if you have an outgroup in this simple case, and so you assume that there was a root, and then there's an outgroup, and the evolution was still the same simple homoplasy model for the outgroup, then in fact you can make a switch. So you can use an outgroup in place. So, but of course in real data the outgroup may be far away, and so you might be less comfortable still with the assumption about the method of evolution.
Right, yes.
You made the assumption that the pseudocycles don't happen, and
Yep.
that somebody else earlier this afternoon said, well, you don't get the. You also made the assumption where the descendants don't go
That's
back
right.
in. Now, biologically, that happens, I think, quite a lot. I've got a dog who's a pedigree golden retriever, and his grandfather and his great grandfather and his
Mhm.
great grandfather are one and the same.
Mhm.
Actually, yes.
Yeah.
Another dog.
Yeah.
It might be the same, but clearly it happens quite a lot.
Yeah.
Have you ever tried modeling with allowing this to happen?
Well, I've tried and I didn't succeed in getting a simple statement. The only place where that was needed was in the existence of the hybrid, the existence lemma. Not the criterion, but the existence lemma. So, in fact, I can make examples in which there is a pseudocycle and the theorem fails. So some other condition would be needed. But I agree it's definitely an assumption, and it'd be nice to replace it.
Anyone else? No? Oh, thank you, Stephen.